Hello, everyone. I'm really glad I'm here. I was born in Krakow. I was going to school in Krakow. I was living in Krakow, working in Krakow. Probably I'll die in Krakow. So it is kind of very nice for me to be today here with you. My name is Jacek, already mentioned, and I work in Revolut. And there is something special we do about event streaming because whenever I actually talk with someone, people, when you say event streaming, they say like Kafka, right? So this is like almost equal. That's not what we do, and I'll give you some details of why we actually approach it slightly differently or kind of really differently. But yeah, just reminder, if someone didn't go there and add the questions there. We'll go through them. And short info on my side. So I'm actually with banking industry for quite a while. I was previously working for UBS, investment banking, EPAM was the same. And I'm almost actually Java-based software engineer. I was doing .NET at the very beginning, but that's kind of the past. It still gives me some different view on some concepts, but yeah. Context. So actually, this is very important to understand why we do things this way. So for us, Revolut is actually a finance services company, which is mobile first. Some of you may be already users. And we give people an easy way through just mobile to deal with their monies, to exchange money. And you probably know, or you may imagine, this is, you really don't want to lose money, right? So this is fairly regulated market. So it's not kind of easy. You develop some stuff, you put on production, and that's it. Now, there's lots of rules you need to meet, and correctness of the domain is a top priority for us. So obviously, money has to actually match, so you don't want to lose any. And another context for us, so we really hugely grow. We have a lot of data to process. We have huge traffic with regular spikes, especially when you run some promotions or when there's some periods, usual periods in calendar. Then we got those traffics, huge spikes of data. And just to give you the view, so when I joined, it was at max around 7,000 new users every day. Now we have up to 50,000 of daily new users. This is kind of growing really fast. And yeah, so that's the context we need to be in. And now why we need the streaming at all. So one of our most important cases is that for any business logics we have, we want to actually do audit for those events happening. So for example, imagine users doing any interactions, and one of our big topics is fraudsters, right? Fraudsters are like typical users, but they are a kind of malicious part of ecosystem. So they, for example, steal cards, they try to hack accounts, and we need to be aware of what's going on and sometimes use these events for example, recognition of some activities like that. Besides of that, the other reasons why we need to have events is like, we need them to be highly available. So then the point of time when, for example, we have, I'll be speaking shortly in use cases, but one of our use cases is when we measure FX risk. What does it mean? So when you exchange currencies between Polish zloty and euro, you always had some risk which is connected with how the rate is changing, right? So, and we put that risk on ourselves, and we had to measure all the transactions and have the way to figure out what's the risk. And do we need to do any hedging, which is kind of buy in the opposite side, so mitigate the risk. So for that, we need those to be highly available so we can actually understand what's going on. They need to be durable. So it's not like you have events, you process them, but we really need to have events for quite a long time because of the market we are in. And one of the additional requirements we had is like whenever we consume some data, we really wanted to have ability to create advanced queries, how we name them, to make them queryable. So we are heavily Postgres based, and there is lots of great stuff about the database. And we, from very beginning, had this thinking about how to analyze data using already created tools. So SQL is great for analyzing data. And if you can utilize that in the streaming, you don't need to go to things like KSQL and others, which sometimes are kind of hard to adopt. And there is a lot of distributed ecosystem happening. There is old plain SQL with Postgres, which is actually pretty good in a lot of stuff. And yeah, you already mentioned that we need to have this streaming solution with all those requirements, with this context scalable. So this is really growing fast, and we have to have a way to scale our solution with demand. The requirements, just to reiterate them, so strong consistency. This is strictly connected with dealing with money. At least once delivered. Again, if transaction happens, you don't want to happen for that to happen twice. Right? That should actually happen always once. High availability and scalability, obvious topic, right? If you are at such scale, you have to have it. But another things which are crucial for us, and they're not always easy to achieve if you would like to have strong consistency and low latency, then that's one of the reasons why we have kind of own solution and why we need this low latency. I already mentioned one of the use cases is analyzing of this risk or recognizing some patterns. For many cases, we have to have almost real time. Obviously, it's not real time, but almost real time. When we measure our latency, usually in majority cases goes below 200 or 150 milliseconds. And yeah, persistence, already mentioned about the need for keeping data for a very long time, and consistency actually is connected with persistence too, because whenever you are at any stage of processing events, it's obviously asynchronous for streaming. At every part, we want to have this persistency there, so we do not lose anything. And I'll talk in a minute how we achieve that. Observability, very actually needed thing, because this system, distributed system, they are very, very complex. You probably know, and if you don't have a way to observe what's going on with the system, how do you react on any spikes I mentioned before, and you do not learn or you do not have arguments how to actually learn how your software behaves, very bad things may happen. So that's definitely something which was part of our requirements. Let's speak now about the design. This is nothing super, fancy. It's like usual microservices design, but it's actually doing quite a lot of good parts for us. And we divided the stateless parts, which are very easy to scale, from Postgres, which is responsible for the state and actually giving nice tools or nice ways to scale it at all. So what we have in here, on the left side where it all starts, we have a producer that's using, so we use our client libraries which wraps API, so developers doesn't need to actually know much of the details of below protocol. So how do we use HTTP? How do we use, if you use, for example, gRPC or socket? So that doesn't matter from them. We hide that complexity or actually details, implementation details over libraries. So all our services, they use them to produce events, to read events. That's actually one of the features, because as we have Postgres already as a part of this event streaming solution, we not only can stream this data, but we can ask for very detailed queries, like GET requests to that, and it's still doable, it's still performant, and you can do that. There are some cases for us where actually it's more preferable to have ability to query for some events than stream them. And finally, we have the consumers. So consumers are at the very end of streaming flow. And we separated, that actually happened recently when we decided to separate event store, how we named the application which is responsible for handling requests for writes and reads, and event stream, which purely depends now on the streaming. Why we divide that? Because actually implementing the streaming alone, and anyone doing that probably knows, it's a very complex thing. And we wanted to separate those things which are, let's say, easier from those which are more complex and have a separate ability to scale them and release, deploy them. On the database side, we use Postgres with master and replicas setup. We do use a few replicas for availability and actually for scalability and handling events and ability for any of those replicas to go down. One of the nice things is that Postgres gives that with the setup that if master will goes down, one of those replicas will take over the role of the master, and you can fairly easily build up new replica. And adding replica is fairly almost trivial, considering amount of data we have. I think we have now around 8-9 terabytes of events for that. The good thing is that we don't need to deal on the Postgres side with topics. Whenever I was going through messaging system, one of the biggest issue was like you had to manage somehow topics. You need to somehow communicate about the topics names, how actually you manage them. Remember about backward compatibility, movements between topics, things which, yes, we don't have this complexity. We have just tables. It can be even simplified. We have two tables, action events and model events, which potentially can be even just events. But there were some reasons why it was created like that. So we keep it like that. It works for us. Mostly we have like, whenever business action happens, we represent that as an action event, and every business action may actually state many changes, change many states of different domains and models representing those domains. That's why a single business action may have many model events. If we go further, so what are the use cases, real use cases? We do use this solution nowadays in production. So I've already mentioned that the audit log of user actions that's used by our customer service. So whenever someone reaches out and they see like something doesn't work or something bad happens for them or just want to verify something, we always have a way to observe what kind of flow directed to that, and we have easier way to mitigate that. But in our cases are figuring out any suspicious activities, because some of the events coming may not actually be expected, and you have a way to figure out that. And that's actually the second use case. So we have real-time fraud detection and event-driven machine learning-based risk scoring model. What does it mean? So firstly, this fraud detection, so detecting whenever something bad happens. I already spoke about that. But besides of that, there is data team, which is, let's say, clients of our solution. They consume events from event streaming, and based on that, they apply written in Python machine learning algorithms, which do a lot of interesting stuff, like risk scoring models for our customers. Then we have automatic real-time FX risk hedging. That's what I mentioned when I said every exchange between currencies connect with the risk, and we have to have a way to deal with that. We don't want to go sometimes bankrupt because we didn't maintain that, and let's say Swiss franc to Polish zloty rate will just rapidly go. Things like that happen. So any company doing these exchanges at some scale needs to do that. The other cases are real-time P&L or automated marketing campaigns, promotions. There's much more cases. I'll not go deeper into that. You may actually get the idea of how it's what kind of the use cases we do use it for. How do we achieve this strong consistency considering these events? And what's important is like if you have transaction, it's like with any banking system, and if you have some producer which communicates about transaction started, then you have event store responsible for storing that into database, and then finally you have consumers which looks for that data and they consume that. At every single stage, you want to be super sure that it moved further and it was saved, stored, or you have to retry. There is no other way, and you need to actually handle all possible failures. So what we do on the producer, and actually Pavel, who was speaking before me, he was doing a lot of implementation into that, so kudos to him. So the models and journal database. So we keep database. Actually, its table is very simple, and using the fact that producer microservices already have databases because they have own models, we add very small event log tables there. And this is responsible for storing information about events. So how does it work? Any business action happens, we store event to our local database, not local, but owning service database, this event, and then we send it. When we send it to event store will get to us the response to handler, so we'll confirm that all is good only when transaction and saving to event store happen successfully. If it not, it will not, we'll retry and we'll be keep retrying as long as event is in the journal. The obvious thing is that we have some retention policy. I think now it's set like 1 day, so we set like policy that during 1 day we have to process those events. That would be very bad if we wouldn't. So if the event was saved, we remove, so we mark the event in the journal on the producer that it was already processed, and we may actually schedule cleanup of that, which happens asynchronously. Interesting cases are about actually the need for handling duplicates. So obviously, it may happen that event store will save the event, and producer will get network failure. It will not get the response. It will retry already saved transaction. That's why we developed that in the idempotent way. So there is every event is represented by a unique ID, and whenever event store, which is actually using Postgres mechanism for finding out if given unique index was already saved. It's very fast mechanism and it's giving us feedback very quickly. So if there's any duplicate, we may just ignore that and go further with the rest. And the very last thing, and I've put the database there. It's the most, I would say, the most pessimistic scenario when consumer really needs to make sure it processes the events, because it always may retry from some point in the time to get back again the events and the flow of the events. But on the other hand, it may store in the snapshot and process locally events from the snapshot, and that will give very strong consistency. Then, yeah, it's like more detailed explanation of what I actually said. So there is a lot of processing which happens. I'm not sure we have much time to go through every step, but what's important in here is that even if there is some failure, even if your service goes down, you do deployment. So in process, your process didn't actually didn't retry the events. We still have reconciliation job running on database, which is checking after some period. I think we gave 1 minute or something like that, and after 1 minute old, events are resent by this process. A very nice thing how it's implemented is that all the producers, we choose somebody, I will not go there, but all the producers may take the role of reconciler. So it's not like single process, which is reconciling the events on publisher. It's like any of those services may take this role. And there is a locking mechanism which we use, which actually gives you a lock for being this reconciler. And that works pretty well. Yeah, and on the event store side, that's what I said. So whenever we have duplicates, we just ignore them. And Postgres or an SQL database has very good natural ways to deal with that. Yeah. So requirements. How we deal with the requirements. In here, at least once delivery. So obviously, retries, they help us on every stage to deal with making sure we deliver, plus uniqueness of the events give us ability to not have more than one event processed. The thing which is not in here, but I already mentioned, is there are background processes which, when your application having duties for retries fails, there is still some jobs which will make it work later on, like this reconciliation on publisher side. Yeah, what do we use on this instance? I already mentioned we use Postgres 11. We use for scaling master and replicas in the same time. We use PG Partman, which means we use partitioning. What do we use it for? We split all the events monthly. So whenever we do streaming, whenever we do get queries, we may focus on periods of the month and make those data flows much faster. So if we wouldn't do that, you would have really this 7, let's say, terabytes of the events in a single table, in single space of the disk. Every time you had to go for all that would be very problematic. How do we actually use Postgres for this streaming? This is thanks to notify and listen mechanism. So Postgres is exposing this nice feature. There is many ways to develop to actually integrate with that, but we use very simple through JDBC. So how does it work? You create the listen subscription, and then every time, whenever we do insert of the event, it's notifying. What's nice about that is that if any of the event stores saves the event to database, then all instances, all replicated instances of it, of event store and event streaming, will be notified. That's a pretty nice way to scale the stateless part, although puts a lot of efforts to scale database. As I mentioned, we use master slave replication. How do we achieve this hierarchy and scalability? Stateless services, asynchronous processing. Some of the technologies actually we use may be interesting. So it's written in Kotlin, this event store. Event streaming is already written in Java. We had some challenges with Kotlin, especially when you get very complex distributed software, which is using coroutines, some multi-threading, and you're using monitoring, which needs to sometimes understand what's going on in your bytecode. It's not always easy for them, and not always easy for us to find out, but we were finding different ways to deal with that, but it's much more problematic. And we use Ktor. Ktor is very nice, neat library from JetBrains. It's for Kotlin development and for asynchronous serving of REST endpoints. And it's quite a lot of using coroutines concept. So I'm not sure if you're familiar with. This is kind of lightweight way of processing asynchronous code without using threads in the Kotlin. Netty, obviously, as many of such solutions, and very recently, initially we were using WebSocket, and Oleg did very good job because he explained all the reasons of why we are moving from WebSocket to ReSocket. Our initial implementation of the streaming was using WebSocket, and we had a lot of problems with building on our own resilience. So back pressure, considering this Postgres server, which is event store, and consumers. There is many parts, many changing parts, which you need to take care over, like back pressure to not kill server, to not kill consumers, and to not kill even Postgres, because if you do not consume, if you block for too long on this notify listen mechanism, you will quickly reach the limits of Postgres, and then nothing will be streamed. It's working very fastly as long as you do not do blocking things, which never should happen. And yeah, horizontal and vertical scaling. So we firstly go with horizontal as much as Google Cloud Platform allows us, and then we go, vertically, and then we go horizontally, which usually make sense. Low latency, how do we achieve? So any communication between consumers, producers, and this event store, they are done within single GCP region, GCP, which is Google Cloud Platform. We obviously use HTTP calling. We use asynchronous logging, and so that's a very important thing. I hope all of you are aware. In my previous job, when I was in Platform Team 2 in UBS, we had quite a lot of bottlenecks, performance bottlenecks in application. And when we started to research that, we realized that I know 70 or 60% of these bottlenecks was coming from synchronous logging. So yeah, lesson learned, never again. And yet, the last thing which we do is Google Cloud Platform has, for internal communication within the same region, TCP-based load balancing. It's very fast. They have some papers on that, how does it work. It's very lightweight in terms of application, and that works pretty well for us. Immutability, yeah, I already mentioned that idempotent is important, but besides of that, we keep our events immutable, as usually do for events. Client SDK, quickly going. So that's how usually it looks like from the publisher side. So you create some configuration, you use some Fluent API to set up your async publisher, and then you just save. Obviously, there's this requirement of database which has to have this event log setup, but that's, let's say, assumed in this case. The fetching, again, quite simple. In here, we, in addition, add the filters. We add the filters based on, that's actually very nice. That's the first thing, because you already may observe that it's giving us the fluent way in Java or any other language to define queries at any complexity you need at some point. Obviously, if you don't need, then you keep it simple, that SQL may expose. So for some cases which we have, like I'll show in the streaming, having this SQL allowed us, especially with Postgres, to do very nice filtering on the streaming. And that's my last example. It doesn't fit, but I may scroll. That's kind of cool. So usually how you implement consumers, so you get some event consumer, you, as usual, set up on event. Then we have interesting stuff happening here. So firstly, we say what kind of model, what kind of domain I'm interested in. So this is like a topic in your, in Kafka or any kind of RabbitMQ solution. But in here, it's like more dynamic. So you have single table, and then you define by which you want to filter. So you have very dynamic, very dynamic kind of topics. Then we say, because every model have many or can have many different events connected with that. So we say like, what kind of event I would like to take. That's obviously maybe just I want to take all the events for a pocket. But in this case, we look for a model created event for a pocket. And the last part, which is very cool, because if we save the events, we use one of the tables is JSON based, and Postgres has very nice setup for JSON. It's allowing even to do queries, indexes, and we use this actually for the goodness of our consumers. So we were able to limit by 5 to 10 times load on consumers, because we said, I'm interested in pocket model created events, but just give me those which has balance 0 and currency 0. And that was quite a big change in terms of the load on our consumers. Learnings, yeah, so retries, yeah, I mentioned a lot about them, and that's one of the trickiest part we learn more and more about, because in this such distributed system, you need to be very careful about, so it's starting at production, living own life. You have to have observability to understand, but if it's complex, it's very hard to follow. And too much retries from wrong reasons may actually kill your infrastructure. They may actually start doing cycles. If you do not recognize them, you will always retry. Or you may, for example, one of the cases we had, there were some business failures which were expected. And if we do not differentiate between business failures and some, let's say, network failures or this kind of failures, we'll be retrying normal failures, which shouldn't be retried. They should be more like reported. And you again go into this circles you don't want to be in. Yeah, RSocket. So I already mentioned, so resilience is actually the biggest challenge for us for network protocol, and RSocket is solving a lot of them. We went to production recently. So far, it's doing pretty well. Yeah, so we'll see how in the time it'll go, especially through some spikes, but so far it's doing pretty well. Network protocol, so that's what I mentioned. So reliability is one thing, resilience, sorry, reliability too. But yeah, back pressure, we had own implementation of this back pressure. And it's not like RSocket is doing that for us. RSocket, in our case, it's allowing us to define that in more like DSL way, so declarative way. It's much easier to understand. And this code is already complex. This back pressure is complex because there's so many different corner cases, and RSocket in this case giving us a bit of simplicity. So you may do a little bit more complex things because the code itself is simpler, which is pretty cool. And yeah, one of the biggest things we need to still tackle. We are doing pretty well and continuously improving on that. And one of the good parts for us is the majority of us is in JVM, and that's something Pavel mentioned. So we have similar approach that our contracts are usually in Java, because you may share that as libraries, and you may write tests against them, and compilation will quickly give you a feedback if anything bad happening. But still, there is a lot of troubles, and our data team is using Python, which makes it a bit trickier. So we still have a lot of work to do on that topic. But yeah, I think that's one of the most complex. And yeah, I think the final one, yeah, monitoring and logging. So understanding in such complex system what's going on when a failure happens. You, for any reason, or you for sure, the biggest actually requirement is consistency. So you don't want to lose any event. So losing an event means we have to understand why it happened. Having own solution, understanding everything about those applications because we wrote them, understanding pretty well Postgres gives us ability to adapt and change system very well. So we have no like things, issues sometimes happen. We didn't have consistency issues for quite a while, but if some will happen, it will be required just us to sit down, figure out the logs, figure out this observability data we need, and we'll find the solution. From my experience, previous experience, and some guys, we were discussing about Kafka, how it will happen in Kafka. If something really bad will happen, so your clusters would have problems with some synchronization, or you would have this consistency problem. I had hard times trying to understand the logs and then trying to understand implementation, what it's doing. But yeah, this is kind of understandable. So that's mostly it, what I have. Obviously, we are in Krakow, we are hiring. I hope you may take some of the lessons from that. I would say Kafka is pretty good, I don't doubt, but at least for us, it didn't fit the purpose. And having own solutions sometimes more costly, but in the long term, we already benefit a lot from the features which Postgres and own solution giving us. So that's mostly it. Thank you very much. Questions, right? So if there are any.
There are many questions. But before we start, we start with the questions, you may want to go to Slido so we can, display them so everyone can see, because there are many of them. And by the way, for the audience, we probably won't have time to go through all these questions because there are nearly 10 of them, 9 precisely. So you may go to Slido and vote for the questions that you want to have, that you want to ask. And the track would be ReactSphere QA, yeah. All right. So I think we may start from the top.
Well, you have chosen Google Cloud over the other cloud solutions. So it's not like we just use Google Cloud. We use Google Cloud and we use AWS for some parts. In the very future, we plan to have like a very same solution both. To not be coupled to any of the provider. But that's not where we start. We start with, I think, Rackspace, and there's lots of issues with that. And after that, and some of the research, things which matters are pricing, stability, availability of data centers near to where we work. So all of that actually went to Google Cloud Platform. So we started both. But Google Cloud Platform in long term won, especially with, I think, the thing of having less, more focused features, and it allows us to focus better. It won somehow, but it's not like final choice. We'll go to both at some point. Do you upgrade event schema change, for example? How? Yeah, we do. We do, and. Yeah, so this immutable is like half true. Thanks to having Postgres, you have ability, obviously, to do fixes on the data. And what we do, so firstly, whenever we have APIs, whenever we have classes, we do usual stuff in Java. So we mark fields as deprecated, we add new fields, but usually we just add new fields. If you add new fields, then it's just a matter of consumers to handle. Actually, there is no, we didn't have any issues with extending that. But there were cases when we had to change, and then it was mostly about updating database. But we only do that for such cases. In terms of applications cannot change data by themselves. And yeah, typical approach for Java classes, because as I said, we keep, at least for now, events defined in Java. How you implement async logging? The question is how to keep the rights order. There is no magic, so we just use asynchronous logging from what do we use? Logback, and we never faced actually ordering issues. So I think it's already handling that on its own. But if you ask about many different services and ordering events by that. Obviously, we do not do that. There's no easy way to actually have asynchronous logging on different machines happening with different clocks. They are synchronizing, but always there'll be sometimes. There are possibilities to move, but with latency we have, amount of logging we do, we didn't face this issue so far. How to disappear questions? Okay. So do we still have a time? Shall I go through more of them?
I'd say that you may answer maybe one more question.
How you implement that was done? How often you replicate database? Is it periodically or on every event? Or so yeah. So I have to admit that till very recently, single master and single replica was keeping a load. It was super good for us, and we didn't have any issues. The problem we started to face is that when you have just one replica and one master, if something goes badly with master, it switches to this replica. And if something happens badly with replica, it goes with all the read queries to master. That's pretty bad. Till some point, we were monitoring and didn't have an issue. But yeah, our data team is very like CPU consuming, and they do a lot of heavy streaming. So we had to introduce 2 replicas, and we isolated that replicas cannot anymore switch to master for a read. That's easy to do with connection URLs in JDBC. And that's it. It works pretty well. Adding new replica is mostly a cost, right? So we monitor the capacity of that. And as long as we don't need it, we don't add it. If we need to add it, we just add it. That's basically how it works.
I think I need to interrupt you at this moment because
Sure.
we need to start preparing for the next presentation. If you have, well, I know that you have more questions because they are there. So I guess feel free, Jacek, to catch you at the hall, maybe after the presentation, so people can ask you the questions. Would you be here for a moment?
Yep.
So catch Jacek outside. Thank you once again.